So today we are finding the directional derivative of this two variable function. So this much we can, this is 3D quadratic surface, so we can kind of imagine this surface is C is equal to f of x and y, two variable function, okay? So let me tell you one more time. Partial derivative with respect to x is the slope in x direction. With respect to y is a slope in y direction. But if I specify u, some slanted direction given by the problem, then can you tell me what that slope is right there? Okay, so this u will be given by the problem, and the picture here is misleading, but u is a unit vector. This length is equal to 1 from here to here. I drew it so that it shows up better. So far so good, as opposed to this h that we are going to talk about later. H is much shorter than u, so they are not the same length, okay? H is infinitesimal, so in fact h is infinitely small. Good. Okay, so let's start with this directional derivative with the direction of u of f function, which I call it duf, is equal to, well, still limit as h approaching 0 of delta f. I used to put delta x, but I'll just put h here. Okay, so it's like dy over dx kind of idea, delta y over delta x idea, except h. Now we have to figure out what h is. H is an infinitesimal movement in the u direction, so h is much shorter than u. Okay, so far so good. And we still have no idea how to figure all this out, but kind of what it is. Okay, so let me write this down. Limit as h approaching 0 of, let me write down the numerator, f of x plus some, let's call this point right there, x naught, y naught, because this is a derivative at x naught, y naught. We fix this point. And then, of course, z variable, z coordinate is 0 on xy plane, okay? X naught plus something, some little tiny thingy. Don't write this down, it's not correct. H maybe? Space, don't write this yet. And then y naught plus h over h. This kind of looks like last year, right? Except we used to have just like one, f of x plus h over h minus, and then here minus f of x naught, y naught. Right? You're saying, what's wrong with this? Here's what's wrong with this. As denominator only varies by h, if you just give x this as an h and that as an h, then this movement is much longer than h. So it's not a fair comparison now, is it? Right? I want this movement, this length to be h, but what I did so far is this is h and this is h. That you cannot do. So far so good. So we have to figure out the correct expression of how much does x increase and how much does y increase. That all depends on this direction u. Okay, so let's just figure out the u vector down here. Okay, u vector, unit vector, that little head usually denotes unit vector. I'll call it just a and b. But what is a and b made of? This is cosine theta, comma sine theta. And theta being this angle right here that this thing makes with x direction. You know what I'm saying? Does that ensure this thing being a unit vector then? Right? Cosine squared plus sine squared is equal to 1, right? You with me? So then just to make sure this thingy magnitude is equal to 1. Okay, so when I say A is cosine theta and B is sine theta. So far so good. Now let's figure out this side. Okay, this side, here's a right triangle. The hypotenuse is h. So this side has to be h times cosine theta, isn't it? And this side has to be h times sine theta a. So this is HA, A being cosine theta, and HB, B being sine theta. How about that? Are you with me? This is very confusing. So if it's not clear, let me know right now. Now is a good time. So up here now, my difference quotient has to be H plus, well, HA and HB is the correct difference quotient, isn't it? You with me? Okay, and then this A is tiny. HA is smaller than H, right? H itself is tiny, but this is even smaller. AH, because this is H cosine theta, H sine theta. You get it? Okay, now, then we are ready. Okay, so if on this movement, we can create a vector here, right? We can create some kind of vector function, x and y. So first, so good. Let's write down this vector function on this line along this line. Would that be this? I'm gonna do this with black ink. Would that be x naught plus AH? Let me write down in different order, AH, and then y naught plus BH. Using H instead of T as a parameter, does that create the equation of the line here? Remember, x is equal to this and y is equal to that. Do you remember the equation of the space line? In this case, 2D, moving along the xy plane. With me? With me? So, then what we can do is, we can let f of xy, but x is a function of h, and y is a function of h along this line that we are moving, right, in u direction. Good? And that happens to be, of course, f of x naught plus AH, and then y naught plus BH. Does that much make sense to you? So what we have created is some kind of f with a single variable h instead of x and y, because if you have x and y, that gives you quadratic surface, all of it. I don't want all of it. If I slice it down with this plane in u direction, it's going to create that curve right there. And this f describes that curve right there. Good. This is, in fact, the intersection between that quadratic surface and this plane. Say yes. Okay. Now, then this thing doof. Okay, this thingy, according to this definition, we can think of it like this: df over dh. How about that? Because this is a single variable function after all, right? However, do you remember chain rule? That is partial f, partial x, and dx, dh, plus partial f, partial y, and then dy, dh. This h used to be t in previous sections, but now we are using h as a parameter instead of t, because we are having h down here. Are you with me so far? Okay. Now, do you remember, well, actually, what is then dx over dh? This is x, right? So this is constant, so this becomes 1, so is it just a? So what we have is partial f, partial x times a, plus, likewise, partial f, partial y times b. See, if you take a derivative, this is x and y. You know what I'm saying? Say yes. Who's confused? Okay, and then if you think about it, this thing looks like a dot product now, doesn't it? Partial f, partial x, partial f, partial y, dotted with a and b, right? And this is what they call the gradient. Del, they read it del f meaning partial derivative with respect to x and partial derivative with respect to y, and a and b, a, b, lo and behold, that's our u, isn't it? So this is our final product. So when you take and where, I need to probably write this down, where this thingy is, I kind of forecasted it last year. That thingy, differential operator, in an operator theory in much higher mathematics, right? That just means take a partial derivative with respect to x and make a vector, and then with a y, and then, right? And this thing itself, del f, is called the gradient vector. Who's confused? You with me? Okay then. Okay then. Now, let's think about this. So this slope will change as you rotate this thing around, right? Because at one point, at the way this picture is drawn, this is a downhill, but the other direction it'll be uphill, and somewhere it'll be sideways and it'll be perfectly zero flat. You know what I'm saying? And this thing is a vector. So let's investigate this vector a little bit, okay? When we say this partial derivative, which is given by this, right? This is what doofus. That is nevertheless still the magnitude of this times magnitude of unit vector times cosine of the angle between, and since I used theta already, let's call it phi. Good. Okay, now what is the magnitude of vector u? Where's the unit vector? So it's gotta be gradient vector times cosine phi. So far so good. Okay, I'm gonna give you a picture. So what does that look like? Say we have this kind of coordinate system. And say we have u in going off in one direction. I'm gonna change that to black color. And then I'm gonna say our u was somewhere here, right? Say our u is in this direction. That I'm gonna put it in red color because I used red. So this is my u. Okay. Now the gradient vector, we don't know where it points, but let's say it points somewhere. So here's a gradient vector. Let's say it points in that direction. Not necessarily that length. I'm going to use blue color for gradient. Maybe I'm going to make it a little bit longer. So far so good. So this is del of f. It's a vector, so it's got a point. It has to have a direction. So far so good. And this angle between the two, this is phi. Okay, as opposed to this theta, theta is the angle of the u with x-axis. So in this picture, theta is right there, right? This is x-axis, y-axis. Good. So, you with me? Well then, remember this directional derivative depends on the direction, right? Well, it's gotta have a maximum then at some point, which is the uphill, right? Can you see my stylus? At some direction, it's going to point down. In our picture, it's negative, but on the other direction, it's gotta point up. This is your maximum value, and this is your minimum value now, isn't it? Right? So this thing will achieve maximum at phi is equal to 0, right? The other way of saying that is this gradient vector will point towards the maximum slope. How about that? Points. I learned to spell. Get it? Is it somewhat confusing? Okay. You make sure you do homework on this section. And I'm going to give you a couple of more notations. The del gradient vector in 3D. This thing, yeah. In 3D, of course, looks like this. I partial with respect to x plus j partial with respect to y and k partial with respect to z. Okay. See, whenever in physics you can differentiate with respect to time, and we can differentiate with respect to space. But when we say space, what direction, x, y, or z? Those are partial derivatives. But when we say space, that means in general all three directions. Get it? Then what does the second derivative look like? Okay, this is known as del square, also known as Laplacian, Laplace operator, which just means the second derivative. And that is just this thingy, right? And remember, this thing is a vector. Okay, so this will look like partial x, partial y, partial z, and dotted with itself. Okay, so if you do that, it looks weird now, doesn't it? It's not a vector anymore. I regret writing it like that. I'm going to squeeze in f, because without the function, these things make not that much sense. So if I put f here, move that over a little bit, and if I put f, and then I need f here. Okay, so there's f here, here. Good. Now we take another. So this is, when you take, this is a gradient vector, and remember this is a vector, and we take another dot product with this, that this ends up being second derivatives added together. This is what Laplacian operator does.